so on to our next speaker. It's Bill Daly. All of the people I've talked about so far, are some of my favorite people, but Bill was my advisor. Okay, so he's above them, right? No, he really is. I had a great time being in Bill's group. Bill is currently with Nvidia. He's their chief scientist and leading research group at Nvidia. So he's doing tons of stuff, just like he likes. And today, I guess he'll talk about some of it.
Yeah, so I'm really honored to be here at Yale's 75th celebration. I think that, it's probably like Yoda. He'll say, when 75 years old you are, look as well you will not. And to sort of reflect on all the great things he's done. But I think things even like sort of inventing out-of-order execution with HPS and modernizing branch prediction and all these things kind of pale in comparison to the students he's produced. I'm always just kind of amazed. I think the real, sort of test of a great professor is the quality of the students that come out of their group. And I think it's hard to find anybody in computer architecture that's produced as good a crop as Yale has. So I'm going to tell you what I'm sort of most worried about today, and I think it actually is sort of, what I think one of the big challenges are for the future. So I spend a lot of time, I spend about half of my time worrying about what I think of as the exascale challenge. And it's really a proxy for a bunch of things. And it's basically, how do we build things that go into the data center and deliver the most performance for total cost of ownership to the end user? And actually the 20 megawatt constraint, and people at the DOE came up with the constraint, have admitted to me, it's not a real constraint. They could build 30 megawatt, 50 megawatt machine rooms. It's a proxy for cost of ownership. So the question is, how do you get an exaflop in a real application at less than 20 megawatts? It turns out I spend the other half of my time worrying about how I can deliver great user experience on cell phones, which is going to require, right now delivering about 50 gigaops on something where you can dissipate about a watt. It turns out it's exactly the same problem. It used to be when we designed high performance machines, we did all sorts of things that were very different. We used a different process, we used a different architecture because we were willing to burn gobs of power to get performance. Today that's not the case anymore because we're we're power limited. And so today, even on the very high-end machines, performance per watt, efficiency is performance. If I can be more efficient, I can deliver more performance because I have a fixed power envelope I'm living in, and that's actually the way we've been designing cell phones the whole time. I have to add that there is a constraint on making it very efficient. We're not allowed to completely screw over the programmer. We can do it a little bit, but we have to make it somewhat easy to program these machines. And actually, the easier the better. The big barrier to adoption of our GPUs in many part of the computing space. I've talked to CIOs of large banks who have chosen not to adopt. And they said, hey, we ran a trial, 10x reduction in cost of ownership for our option pricing applications. We're not going to do it because we value our programmer time more than that 10x in reduced power bill and cost of hardware. So where are we today? This is sort of one snapshot. This is the Titan machine at Oak Ridge National Laboratory. It's the fastest supercomputer in the United States, second fastest in the world. And the GPUs that it's based on, the Kepler, this is a Kepler K20s, the K40s out now, hold all 10 spots in the top 10 of the Green 500 list. In fact, it goes down way further than that. There's the other chips don't even come close to it. So everybody who put an entry in with the Kepler in the Green 500 list is in that top section, and then the Intel Phi guys are somewhat below that. And the number one on the Green 500 list is this machine, the Sobami KFC at Tokyo Tech. And they got the efficiency to be almost twice what the Titan machine is by doing two things. One is booting out a bunch of the CPUs, because they burn a lot of power and actually don't contribute very much to solving the problem. So they have a much higher ratio of GPU to CPU. And then they went to this exotic cooling system, and this is why I think they call it KFC, because it's very much like what they do at Kentucky Fried Chicken, where they put these GPUs in hot oil. Well, the oil wasn't hot until they put the GPUs into them, and by doing that, keep the junction temperatures down so they leak a lot less. So I was in Washington a while back. I actually got summoned there by some people in the Department of Energy to answer for some things. But while I was there, they asked me, well, could you build an exaflop machine today? And I said, well, what do you mean by an exaflop machine? And they said, well, something that could execute 10 to the 18th floating point operations per second. I go, well, no problem. And I just sort of got a napkin out and I sketched this, which is you have a 1 centimeter chip, centimeter on a side, and you just fill it with double precision floating point multiply add units. They're about 1/100th of a square millimeter each. In fact, this is not to scale. If I made it to scale, you wouldn't be able to see it. And so on this chip, you can get 10 to the fourth of these, sort of, a 100 by 100 array of these floating point units. And they, running at a gigahertz, they deliver 2 gigaflops each. You get to count the multiply and the add as ops. And so this is a 20 teraflop chip that dissipates about 200 watts. And you just put 50,000 of these into racks, and probably take about 50 racks or so. And no problem, actually, for way less than what they pay for a supercomputer today, I could deliver them an exaflop. And it would be completely worthless other than as a space heater. Because the problem is not the flops. I mean, much like children or pets, the cost of a floating point unit is not acquiring the unit, it's feeding it and disposing of what it produces, right? And so you have to provide instructions and data to these things, and they produce results, and you have to do something with those. And in fact, when I look at the real challenges, whether it's the cell phone challenge or the exascale challenge, it boils down to 2 things: overhead and locality. And so let me deal with those in order. Let me start with overhead. It's interesting. So back in sort of the 1970s, we gave lots of students PhDs for coming up with clever instructions and adding them to instruction sets. And then in the 1980s, we sort of were running into a limit in that, so we gave students PhDs for taking them out. We called that risk. And I think we've sort of going through an evolution of that, where we gave students lots of PhDs for inventing complicated things to put into processors to make them go faster if you didn't care about power. And now we're entering an era where we're going to give students lots of PhDs for taking those things out and making the processors simpler so they are more power efficient. So here are some pie charts from a couple papers about where power goes in different machines. Mine is the one this is the paper I wrote on embedded processors. And even in very efficient in-order embedded processors, the study we did on a SPARC Leon, only 6% of the energy goes into ALUs. And actually, most of the things we're counting as ALUs were doing what I would call overhead operations. They were basically updating the branch end, the loop end condition. They were calculating addresses. The payload ALU operations, the things you would count toward ops in a real algorithm, was maybe 1 or 2%, even in what's considered a very efficient in-order core. And this is why special purpose hardware today can do so well, is it just gets rid of all this stuff by making it not programmable. And out-of-order core is far worse. This is some data from a DEC alpha. And again, it says 4% ALU. The payload ALU is a fraction of a percent. So the real situation, if you look at a modern out-of-order core, is it's kind of like this. The overhead part, the stuff which is not payload, is 980 picojoules out of the roughly 1 nanojoule per instruction, which if you ignore the SIMD extensions on processors, modern high-end processors are around 1 nanojoule per instruction. And we know that doing the arithmetic op takes about 20 picojoules. That's, by the way, if it's a double precision floating point op. A 32-bit integer op is a fraction of a picojoule, about 0.3 picojoule for an integer add, and the overhead ratio is much worse there. And that's because these machines look like this. This is the alpha diagram. There are actually some execution units here, but the bulk of the power is not spent in those execution units. It's basically spent, queuing things up and scheduling them and doing all the stuff that could be done in the compiler once at compile time. You do over and over at runtime to large expense. In GPUs, we build data paths that look a lot more like this and are able to be much more energy efficient. And doing that, we have results. I won't go into a lot of detail here because I have a limited amount of time, where we can make that pie roughly 50-50. So for floating point operations, at least, there's very little need to actually build a special purpose processor, because we can drive the overhead of making it completely programmable down to about 2x. That's not true for integer applications, because what you're doing is, for example, in signal and image processing, where you're doing 16-bit integer operations, that's not 20 picojoules on this side, it's 0.3, and now you've got an overhead that's still over 100 to 1. So we know how to drive the overhead down. Remember, the things that are driving our costs up are overhead and locality. Let's talk about the locality. So here's a little bit more complete picture of my real die, and what you see is this cost of feeding our function units with operands is pretty expensive. So a 64-bit double precision floating point unit is 20 picojoules per op. To feed that op requires 256 bits, a 64-bit instruction, and 3 64-bit operands for A, B, and C, for the A times B plus C. If I get that 256 bits, so there's 3, and then I produce one result for 4. So the 256 bits is input plus output to this. Even if I keep things very local on the chip, and our GPU chips are big. The current ones are well over 500 square millimeters. They're basically an inch on a side. And even if I keep it very local, within 1 millimeter of that sort of, it would be 50 to go to the opposite corner. I'm going to burn more energy moving data than I am doing the arithmetic operation. And by the way, the data didn't just materialize on the end of the wire unless I wanted to sample noise. I had to read it from some memory array, and reading 256 bits, even from a very small memory array, is more than twice the power of doing the operation. So reading it, transporting it locally, I'm already many times the operation. If I have to go global on chip, it's orders of magnitude higher. If I go off chip, it's 2 orders of magnitude higher. So when I tally up what it's going to take to get to exascale or to build efficient cell phones, what it boils down to is what is the sort of working set profile of an application. The locality challenge I can sort of sum up in this chart, and I'll take a minute to explain it, because when I sent these slides around to a couple of friends of mine to sort of critique, I said, what on earth is this chart showing? So the x-axis here is sort of how large a memory you have at different levels of the hierarchy, and the y-axis is how many bytes per flop you need to get out of a memory of that size to keep the program running. And this is very dependent both on what the application you have is, and also, as I'll talk about a little bit later, how you have scheduled that application. There are ways of rescheduling applications without changing the computation you're doing that can dramatically make this better or worse. It's actually quite easy to make it worse. You just take the instructions that would reference data and you move them as far apart as possible. The making it better is trying to figure out what's going to reference the same data and grouping it all together to enhance your temporal locality. But you get, you basically have to get, for most of the kernels that I looked at in sort of producing this composite chart, 1 word of the 4 you're using for the floating point operations out of something order of 1K in size. You can start driving you get enough reuse out of that 1K size buffer that you can drive it down to where you only need to get about 1/4 of a word out of a 32K byte size thing, somewhere around 1/8 of a word out of a meg, and the fraction of data that you need to get from different levels of memory goes down as you move to the right. Now, there are some poster child bad applications where this is just 8 flat across the top, right? You're just walking through all of memory and doing something. And there are other ways of dealing with those applications that have to do with moving the computation to the data. But for most applications, there's curves that look roughly like this. And then what you do is, that's basically plotted on the left axis here in units of bytes per flop. That's a characteristic of the application and how you've scheduled it. The next line to look at is the blue line here, which is what did that cost you, the picojoules per byte. It costs, and that's over here, it costs relatively small picojoules per byte to get stuff out of the local memory. Remember, the local memory was 20 picojoules to get 256 bits out of that. It's 32 bytes. So it's actually somewhat under a picojoule per byte to access that memory. But it goes up dramatically, and by the time you're referencing DRAM, you're up to around 200 picojoules per byte to get stuff out of this. And even sort of the last level on-chip memory, you're around 30 picojoules per byte. Now, these are today's numbers. If you look at how things scale going forward, this is the energy shopping list. I gave a talk at Nvidia a while back when I sort of was cajoling people to take energy more seriously, which we do now. And one of my analogies was you wouldn't go around the grocery store throwing things in your grocery cart without knowing what the price tags were on them, because if you did, you'd get to the checkout counter and you'd either immediately be carrying a lot of stuff back or negotiating a loan. But we actually were designing things that way until we started becoming very energy conscious. Now we actually have a price tag on everything, which is how many picojoules it is to do that thing. And this is a little bit of an old chart. This is a couple generations of technology back. Back in 40 nanometers, doing that DFMA was 50 picojoules. And you'll see scaling to 10 nanometers, and our exascale machine will probably be in 7 nanometers. But even scaling to 10, we get this nice 7x gain. In fact, all of the sort of logic things and memory things up there are roughly 7x from the 40 nanometer column to the 10 nanometer column. Moving bits is less than a 2x advantage. So even though moving bits was already the problem, it's becoming more the problem because the other stuff is scaling. But moving the bits really isn't scaling very well. The capacitance of a wire has been roughly constant at 200 femtofarads per millimeter through many, many generations of technology. It's one of these things, as you scale the dimensions, they all cancel out and you wind up with the same basic unit. and hence the cost of a transition, since we've been kind of stuck on a 1 volt supply for a while, is roughly 200 femtojoules per full cycle, up and down, so about 100 femtojoule per transition per millimeter. Now, so if you really want to make efficient machines, you go back to this chart. What we need to do, since our total power, which right now is around 77 picojoule per flop, so I really don't care about the 20 I'm spending on actually doing the flop. It's the 77 moving things that matter. That's basically multiplying this line by this line, which gives me the orange line here, which I'm showing times 5 to make it line up on this scale. I need to make that smaller. I'm going to do it in 2 ways. One is, it's kind of like when you go see the doctor and you say, my arm hurts when I do this. He says, don't do that, right? So I'm going to move the data less. But then when I do have to move it, I want to move it more efficiently. So how do I move data more efficiently? This is a plot out of one of my former PhD students' thesis. And what it's showing is sort of what it costs to move a bit per millimeter. And what most people do is the black line here with the circles. And he called that full swing signaling. It's kind of the worst possible signaling system. You use ground to represent a 0 and 1 volt to represent a 1, and you drive the line with an inverter, to basically to full logic swing. And the reason it's the worst possible signaling system is that your energy is CV squared. You're using an enormous amount of voltage. In energetics, 1 volt is an enormous amount of voltage. So you're using an enormous amount of energy to send this bit, and you don't have to. These 3 things were sort of the prior art he was competing with. And this was his PhD thesis, which is around 30 picojoules per bit millimeter. And he fabricated a chip and demonstrated this and such. And we're actually pretty confident that we can get this down to maybe to the 10 to 20 picojoule per bit millimeter range, which is basically an order of magnitude reduction in the cost of moving bits. We have similar results for off-chip. We had a Best Paper award for the Best Paper in ISSCC 2013 for this work, which was basically moving bits off-chip. And the concept is really simple. The way to do this, you need to do a voltage conversion and drive the wire. And you can combine those 2 together by basically charging a capacitor, disconnecting the 2 ends of the capacitor. It's easy to build these switches with MOSFETs. And then connecting it back to the line. And if you want to send the other bit, you connect it back to the line upside down. And it actually does exactly the right thing. You get an efficient voltage conversion, and you drive the line with exactly the amount of charge you need because you size the capacitor to do that. And it produces really pretty eye diagrams. This is at 20 gigabits per second. We threw it on. We actually put these on GPUs because we wanted to demonstrate that even in the presence of noise, and the best way to make noise is to get something that's cranking away rendering triangles at an enormous rate, we could basically make this work quite reliably. And it basically reduces the cost of sending bits from today, which is anywhere from a GDDR5 interface is about 20 picojoule per bit, to some of the more efficient SerDes around 5. This is a half a picojoule per bit. So again, a 10x reduction in energy moving things off chip. So if we look at that and factor it in that all of the DRAM energy is not moving bits, there actually is this row access you have to do somewhere along the line. With better circuits, we can drive our 77 picojoule per flop down to 18, and now we're at least in the ballpark. Now less than half of our energy is moving bits compared to the 20 we're doing otherwise. The other thing we need to do is move stuff less often. Well, how do we do this? What we have to realize is that a lot of the data movement is there because somebody wrote the program in a way that was simple for them to understand, which often is not the most efficient way to schedule it for spatial locality. And the great example here is we were working with a fluids code written by some folks in the Stanford Aero and Astro department, and we were looking at the code, and what it did is it walked over the entire data set and computed flux in X. And then it walked over the entire data set and it computed flux in Y. And then it walked over the entire data set and it computed flux in Z. And then it walked over the entire data set and it took all of those fluxes and updated the pressure in the cell. And then there was one more pass. So it made like 6 passes over the entire data set. And the code was written in such a convoluted way because these people were making low-level optimizations. It was actually kind of hard to discover this for a little while. But once we did a simple rewrite of the code where we kind of blocked their stuff into appropriate procedures and scheduled it so we did one walk over the data set, and for that little block we did all of those 6 steps, and we reduced the memory accesses to the DRAM by a factor of 6. Now one of the reasons, and I guess this was what Arvind said in his first talk, is that it's hard, people think it's hard to program these parallel machines. A lot of the reason why it's hard to program them is people wind up sort of trying to optimize these minute details in their code, making it impossible to read their code, making it impossible to see the things you really want to do to get it right. So the argument I'll make in my remaining couple minutes here is that parallel programming ought to be simple. This is a fragment of a parallel code to do a molecular dynamics computation. The real code to do molecular dynamics computation is hundreds of pages long, right? It wouldn't fit up here. But this is basically what it's doing. It's saying for every molecule, find all his neighbors, figure out all the forces you want to apply to him, apply those forces and sum them up, right? And then there's another little piece of code that pushes the molecule with those forces. So you understand this pretty quickly. It's because there's no machine details, and I'm expressing all of the parallelism. There's billion-fold parallelism here because I got lots of molecules and he has lots of neighbors. And probably the most important thing is that the synchronization is all implied in the semantics here. I'm not doing locks or barriers or any of these other things, which are amazing ways to shoot yourself in the foot or other vital parts of your anatomy. This is, in fact, how to make programming hard. There are a lot of people I know who, they're very smart people, but they're somewhat insecure. And so when they come up with a design, they try to make it as complicated and bizarre as possible so everybody will appreciate how smart they are to be able to get such a design working. And I say, no. You're smart when you can make it really simple, right? But they do things like forking threads and locking things. So it turns out Jim Laris wrote this program to find synchronization errors in software, and they ran it in every piece of Microsoft software they ran it on. It found synchronization errors. And one of the most common ones was you would acquire a lock, because you knew you had to lock something before doing, and accessing a shared data structure, but you'd acquire the wrong one. You say, hey, I acquired some lock, And then there's, of course, no checks to make sure you have the right lock. And so what this really is something that I learned when I was coaching youth soccer, and I found that the most important coaching I could give was to yell from the sideline, don't steal the ball from her, she's on your team. And what this really is an issue of playing position, right? We all have roles here. We need to stick to our role. The programmer's role is to express all the parallelism, to express locality in an abstract way, and then to trust the tools and the architecture to do the right things. Now, the reason why the programmer is always stealing the ball from the other two players is that there's a reason why the programmers don't trust tools. Very often the tools let them down. But if we can do a better job on the tools, and what the tools really want to do is do a combinatorial optimization where they can discover, if you've expressed the program in this abstract way, they can discover that you're making 6 passes over the data set in the naive thing, and they will actually do the reorganization. It's a simple semantic transformation to map, because you've expressed all the parallelism. You haven't said what order to do that in. You can decide what order it happens, what happens in time, what happens in space, and to do that happening in time in such a way that maximizes the locality. You decide where to put things, how to stage things up and down the hierarchy, and what mechanisms to use. And it's painful for architects to hear this, but the real role for architects is to get out of the way, right? You want to expose all the resources in the machine, all the function units, all the memory, and have the simplest possible, fastest possible mechanisms that don't dictate any policies that the tools can map to. In fact, our vision for what a programming system here is that we will write target-independent source code. You won't have to tune your code for a GPU or a CPU or whatever the target is. You will express all the parallelism, express all the locality, and then we will write a bunch of mapping tools that will adapt that code to a target-dependent executable. And you'll map it very differently depending on what the target is, because you'll have different size memory hierarchies, you'll have different numbers of threads you need to fill, and then you'll have profiling and visualization tools. So if things aren't quite as fast, and we like to get on the naive code within 50% of the best you could get, but for the people who want that last little bit, you don't want to ever go back and modify this code. Instead, you want to basically give some mapping directives to tell the tools, don't map it that way, map it this way. So our hope is, with this, we can lop another factor of 2 off. Basically, this line on how many bytes per flop you need out of each of the levels moves down somewhat. And it's not even, but it averages out. You get basically a factor of 2 out, and we're down to 9 picojoule per flop. And that, with the technology scaling that I haven't gone into, will let us meet both the cell phone challenge and the exascale challenge. So to kind of wrap up here, we're power limited from cell phones to supercomputers. Today, if you're really worried about building machines for performance, what you really need to do is build machines for efficiency. Perf per watt is performance. There are 2 ways to do this. Interesting, my little charts were supposed to be here. The first is to reduce overhead. Right now, the payload is blue and the overhead is orange. It's kind of like a big corporation. There's actually one guy down in the basement doing real work and lots of executives in suits talking about the work he's going to do. What we need to do is make it at least look like this, where half the guys are doing the real work and half the guys are talking about it. The next thing we have to do is realize that even after we've beaten the overhead down, today the cost of data movement is far exceeding the cost of doing the operations. And we need to address that both by making moving data less expensive. We can go from 200 femtojoule per bit millimeter to 20 femtojoule per bit millimeter. It's a 10x reduction in the overall energy. And then we can make the software schedule things in such a way that we discover when you're moving things 6 times as much as you need to and just don't do that. And I think that this is, to me, one of the big challenges here, is to build tools that programmers will trust to do this. That is a challenge worthy of a lot of computer scientists spending the next 5 to 10 years on. But I do believe that, and I guess this is why Arvind said to ask me, that parallel programming is simple, and we tend to make it hard by having humans do things that humans weren't meant to do, like synchronization with locks, or deciding what order to take a big parallel for all and map it to a particular architecture. And if you look at the tuning people do to their codes, they're not operating at that strategic level. They're down in the dirt. In fact, if you look at what compilers do, they're down in the dirt as well. I mean, they tend to be optimizing little blocks of code, and what we need to do is move up to the high level and build tools that will take these target independent programs and map them well. So I apologize for running a couple minutes over, Matan, but I got you back on schedule in the other direction.